All right, hello everyone. So today we're looking for a solution to a multivariable calculus 3 problem where we have find du of x sub 0, I hope I'm saying that right, that's the directional derivative at the point x sub 0, which is given as 1 comma 1 comma 3 in the direction of the vector u for the function f of xyz 3xyz plus 1 over xz. The tool that I'm going to be using here is this theorem that says if your function is differentiable, you can find the directional derivative by finding the gradient of your function at the given point, dotted with the direction normalized, meaning you make your direction, your vector that's given, you make it into a normal vector. All right, and that's like the shortcut to the definition of a differential derivative, which involves like a limit and such. And in this case, our function is differentiable, and for most cases in this class, that's how it's going to work. You're going to be working with a differentiable function, okay? But there's certain cases where your function is not differentiable. You would then try to use the definition of a directional derivative. But again, we won't touch on that because that's a whole other topic here. All right, so let me start by finding the gradient of my function, and the gradient is equal to the partial derivatives of all your independent variables and then evaluated at the point given. So in this case, f of x, y, z is going to equal 3xy, z plus x to the minus 1, z to the minus 1. And I'm going to have to take 3 partials because I have 3 independent variables here. So starting with fx, I would have 3yz minus x to the minus 2, z to the minus 1, or 3yz minus 1 over x squared, z to the first. Okay, let me make this point. If you look at the function that I had here originally up in red and the one down here, yeah, I rewrote the fraction as a product of 2 negative exponents, so that 1 over xz becomes x to the minus 1, z to the minus 1. And the reason I'm doing that is because when you're asked to find a derivative, it's a lot easier to write it in the form x to the minus 1, z to the minus 1. And once I take my derivative, I am going to put that back into that fractional form just because we're going to be evaluating points in a sec. All right, so for fy, it's going to be 3xz, and that's it. And then fz would equal 3xy minus 1 over z squared x. Okay, so I'll let you check that. And we're just going to plug in our points in that are given to us, which was the point 1, 1, 3. For each of our partial derivatives. Okay. So this would be 3 times 1 times 3 minus 1 over 1 squared times 3. Next one would be 3 times 1 times 3. And last but not least, I have 3 times 1 times 1 minus 3 squared times 1. Okay. All right. So if you computed all these numbers out, you would get 9 minus a third, which would be like 26 over 3. This would be 9. And let's see, 3 minus 1/9 would be 26 over 9. So our gradient at our point 1, 1, 3 would be 26 over 3, comma 9, comma 26 over 9. And then what you have to do is you have to form for the vector, the vector part of the definition where we have u over the magnitude of u. I'd have to go ahead and find the magnitude of 4, 3, negative 1, which would be 4 squared plus 3 squared plus negative 1 squared. So that's 26, and you would take your vector 4, 3, negative 1 and multiply it by that. Sorry, by 1 over 26. And finally, when we find our directional derivative. We would go ahead and take our gradient value of 26/3, 9, 26 over 9, and then dot it with 1 over square root of 26, 4, 3, negative 1, and you would do a dot product, and you would come out with that number. And that number basically describes the rate of change of your function at that point in the direction that you're going in, okay? All right, well, I hope this helps. Thank you for your time.